Okay, welcome back, guys. Welcome back. Any questions? All right. Yeah, there. Okay. So the last thing we were talking about uh was the data path and the controller. And sorry. It is recording. Yes, it is recording. Awesome. Okay, so the last thing we were talking about was data path and controller. I showed you kind of different things, and then you saw that the way it works is that we add these different components to the system, and then we add these control signals to kind of decide where the data goes and how the data is basically being moved. The last thing that we wanted to talk about was the control signals. If you remember, I said that these are the control signals that we care about. Read write was for the register file and deciding whether or not you want to store the results back into the register file. ALU source was deciding between immediate and register number 2, RS2, and immediate. ALU op and ALU operation, as you're going to see, there are two different things. But generally, ALU operation is a 4-bit thing that decides what operation does the ALU need to do, whether this is an AND, an or subtract, or add. The memory and memrise are for the data memory to decide whether you want to read from the memory or write from the memory or none of them. Mem2reg was the one that decides whether we want to use the data that is coming from the memory and write it to the registers, or use the ALU result and write that to the register. And lastly, PC source was basically deciding whether you're using PC plus 4 or PC plus offset as your next PC. Okay? And then again, to remind you, we are just focusing on these 10 instructions. So if I want to add support for other instructions, I need to add more stuff to my data path and my controller. So for example, if I want to jump to, instead of jumping to PC plus offset, if I want to jump to register source number 1 plus offset, then I basically need to kind of change stuff here, right? And I need to somehow create RS1 plus offset in my data path. I may need to add additional controller signal and all that. Similarly, for example, if I want to do things like excuse me, store byte or load half word or things like that, I need to, for example, change the stuff here, right? So there are things that needs to be changed as we add more and more instruction. That's why the number of instruction that any processor supports is kind of equivalent of how much overhead and how much data, how much hardware you're adding to the system. We specifically, to make things simpler, we just focus on these 10 instructions, but just keep in mind that in order to support the rest of the instructions, you need to add more things to the processor. In fact, we're going to ask you questions in the homework or quiz or project to, if I want to add, for example, jump registers. So if I define a new instruction or use an existing instruction that is not being supported in the system, what are the changes? And you have to actually kind of redraw the data path and controller and show us that. Yes? Uh-huh.
So when you got the pseudo instruction,
Uh-huh.
basically translated like to coding like actual instruction.
Yes. Yes. So the question was about pseudo instruction, and say if I have a pseudo instruction, what happens? The pseudo instruction, when the machine code is being generated, it will be generated based on one of the existing instructions. That's why there is the difference between pseudo instruction and instructions. In pseudo instructions, you don't have support inside the microarchitecture for pseudo instruction. So there is nothing that understand what is like, for example, a move instruction. Move is going to be implemented as an add I, and then add is already supported. Yeah. Question is, during what process is that transformation from pseudo instruction to instruction is done? Whenever we are generating the machine code. So this is an assembler basically is doing that. Yeah. Okay, so the question is that are the pseudo instructions generally slower than regular instruction? If it's a one-to-one mapping, then there is no difference. If for one pseudo instruction you need to create multiple instructions, then of course it's going to be slow. So, okay. So let's talk about these, like how do we design our controller and how do we assign the value to these signals, okay? Remember I told you that we are using an FSM, right? FSM is kind of the sequence of kind of states and then state transitions. Typically, the way that we design an FSM is we list all these control signals that we want to assign. So in this case, the list is here. We, in the initial stage, in the first stage of the FSM, we usually initialize everything to 0, okay? And if you remember, I told you that things could be active high or active low. In the controller, it's the same story. If we have what we call active high, it means that if the controller signal is 1, it is active. If it's 0, it means that it's the default value. So the default value for an active high is always 0. And then if you want to make it active, you make it 1. So for example, if I want to write to the register, I make this equal to 1. If it's 0, it means that I'm not writing to the register. This is what we call active high, which means that it's active when it's high. We're going to go with active high, but keep in mind that there are lots of designs that could be active low. There's no difference. It's just a contract, okay? So as a result, we start with assigning everything to 0. So all the values are 0 by default. Then based on the instruction and the opcode, you decide what to do with each of these control signals. Okay? How do we do that? We basically, as I told you last time, in order to decide the activity of the instruction, there are 3 things that you need to use. The opcode. For some instruction, you also need func3 and func7, okay? In order to make our controller simpler, we make this into 2 separate pieces. We call it the controller and ALU controller, okay? The controller just takes the opcode, okay? So basically only understand the difference between instructions at the opcode level. As a result, the controller cannot distinguish between add and sub or add and or, okay? Because add and or has the same opcode. Add and sub also has the same opcode. In order to distinguish between them, we need to read func3 and func7, and that's done in the ALU control, as I'm going to show you in a few slides. Okay? So, and then why are we doing it in 2 steps? Because this makes things faster, because this reduces the number of states that we need to cover in our state machine in the controller. And then ALU control can basically just go further than that. All right? So let's actually look into this. So as I said, this is basically how this is looking like. So as you can see, I'm using a controller and an ALU controller. Okay, controller just takes the 7th bit, which is the opcode. The ALU controller takes func3 and func7. In our case, since we are only supporting add and sub, the only bit that is different in func7 is the bit 30th, okay? So if you look at here, this is func7, okay? As you can see, everything is the same. The only thing that is different is this bit. This is bit 0. This is bit 30th, okay? And func3 is this bit here, okay? I think it's 12 to 14. So as you can see, what we are feeding to our, sorry, it's 12 to 14. What we are feeding to our ALU control is the 6th bit of func7, which is bit 30th, and then the func3. We are feeding that into our ALU control. We also, from the controller, we are feeding a 2-bit value. This is 2-bit. If we feed this 2-bit value to ALU control, this is to kind of tell the ALU control that this is R type or I type. I'm going to show you that later. And the result of this thing actually goes inside the ALU. So that's how we actually generate the control signal for ALU. Everything else is done by the controller. So we have memread, mem2reg, memwrite, ALU source, regwrite. Also, if you remember, very last thing that I said in the previous lecture was we also simplified the design of our ALU source. Remember, originally I showed you that this is your ALU source, okay? But ALU source needs 2 things. One is that we need to know that this is indeed a branch instruction. And the second thing is that we need to know whether, since we are only supporting branch equal, we need to know that this RS1 and RS2 are indeed equal to each other, okay? In order to support for both of those conditions, we create this AND gate, which basically takes this branch. This branch is only equal to 1 when the opcode of the instruction is branch equal. And then this bit is basically coming from here, and this is only equal to 1 when RS1 and RS2 are equal to each other. Basically, what we do is that we do RS1 minus RS2. If the result is 0, it means that they are equal. So that's what we do here. And the result of that is your selector of that multiplexer. Okay? So just keep in mind that in our controller we use this we use this branch and PC source kind of interchangeably. So PC source and branch is the same thing in this case. Okay? All right. So we're going to fill in this table together. So these are all the control signals, and these are all the type of instructions that we have. Again, from the controller perspective, these are only groups that we see. Within the R type, we have the sub and an add and an AND and so on. But opcode wise, these are all the same. Yeah, you had a question. Yeah, so the question is, if I have a bunch of different branches, what should I do, right? So you would need to then change the controller in some way that it's all able to distinguish between the branches. You also need to update the ALU operation. For example, if it's less than, you need to do some comparison and so on. So there are 2 things that you need to change. Again, it's not supported here, but again, it would be, for example, a homework question that, oh, provide the support for branch not equal. How would you do it? Yeah, you probably can, for example, change the AND gate and so on. I'm not going to specifically explain it because we're going to give it as a homework and you can try to think about it. And then you can later ask the question. Okay. All right, so let's fill this table together. So let's look at the each one and then go row by row, okay? So for R type, let's think what should be the values of these guys. We put either 0 or 1, okay? So for R type, what should be the value of regwrite? Anyone wants to suggest? Should be 0 or 1? Yeah. Is it 1? Why? Exactly. Since you have to finally store the results back into RD, you want to issue 1 for regwrite. What about ALU source? ALU source? Anyone? Which one was ALU source? Yeah. Yeah, ALU source was the one that decide whether you're picking this guy or this guy. And as you can see, 0 means that you're picking this. And R-type operation, you're selecting two sources from register 1 and register 2. Okay. What about branch? 0. Mem read? 0. You're not reading from memory. Mem write? 0 as well. Mem to reg? Mem to reg is this one. 0 or 1? Mem reg is this guy. 0, right? Because you want to select this path, which is coming from the ALU. So you want to store the result of the ALU back to your register file, right? So this one has to be 0. What about ALU operations? We're not gonna talk about it yet, okay? So this don't worry about this one yet. All right, so I-type. Reg write. 1, because we still want to write the result of the operation back into the register. ALU source. 1, right? So that's the major difference between I-type and R-type. That in I-type, you select an immediate and the register. In R-type, you select 2 registers. Rest is the same, right? So it's essentially the same operation throughout. What about load word? Should we do register write equal to 1 or 0? Do 1, right? Because you want to store, you want to read something off of the memory and write it to your RD. So you still want to write it to the register. What about ALU source? What about this one? 1, because you want to basically compute the address, which is RS1 plus the offset, right? So in order to compute the address, you need the immediate value. So it has to be 1. What about branch? 0. What about mem read? 1, because this is the one that you actually want to read. Mem write? 0. Mem to reg? 1, because this time you want to actually indeed select from the memory, right? So you want to read it from here. Okay, so store word, reg write. 1 or 0? 0. You don't want to write it to the register. You want to actually read from register, write it to the memory. So you definitely don't want to store any results. ALU source. 1, same story. Offset plus the register 1 is your address. Branch. 0. Mem read. 0. Mem write. 1. What about mem to reg? Doesn't matter technically, right? Because if the mem write, if reg write is 0, doesn't matter what you provide in this line. Okay, I can provide any random thing as long as I don't write it, I don't do it. But since I told you that we are doing it, the default value is 0, we put 0. But here essentially it doesn't matter. We can also put 1 and it's the same result. Okay? Any question here? Great. Last thing, branch, reg write. 0. We're not writing any results to the register. ALU source. 1 or 0? What do you want to feed to your ALU? 2 registers, so ALU source should be 0, right? You want to put RS1 and RS2. What about branch? 1, obviously. Mem read? 0, you're not dealing with memory, so 0 for mem read, mem write. Mem to reg? Again, doesn't matter because you're not writing to the register, so you can put 0 or 1. Okay? So this would be your table. Is it the same? Yes. Okay? Any question here? Any questions? Okay. So let's finish this part then. All right, so for ALU, we need to generate the ALU operation. So let's revisit what are the instructions that we are considering. We are considering add, sub, and or. We have load and store, we have branch equal, we had addi, andi, ori, okay? So what are the operations that we need to use, and which one do we know? So essentially we need a control bit for ALU operation to decide. We go with 4 bits because we want to support later instructions as well. So we be able to do 2 to the power of 4, 16 different operations is what we're going to do with the number of bits that we're going to use for ALU operations. Just keep that in mind that we put 4 just because we want to add more instructions if you want to. So what are the unique operations that we care about? So obviously for add and addi, we need to do add. For subtract, we need to do sub. For and andi, we need to do and. For or and ori, we need to do or. So these are the R type and I type instructions. Then and then the question is, what about store word, load word, and branch? What are the operations that we need for these guys? For store word, what do we need to do? Add, right? So we need to basically add the RS1 plus the offset. What about load word? Same thing, add. And then what about branch? Sub, right? So we need to do sub. So essentially you need 4 different operations in total, right? So you need to do add, sub, and or. That's all you need to do for this particular one. So 2-bit would have been enough in this particular case, but as I said, in future we want to add more things. That's why we do 4 bits. Okay? So this is basically what this table is trying to show you. That, you know, for load and store, we do add. For branch equal, we do subtract. For R type, we might do one of these 4, right? So this is kind of like help us to make this design simpler. Because if we see R type and I type, that's when we need to go deeper. But if you see anything but R type or I type, it means that we're going to either do add or sub. And that's kind of is going to stay the same for future as well. So based on this kind of operation, there are 2 options for our ALU operation. Okay. Option number 1 is we feed everything to the controller, opcode, func3, func7, and then we generate one ALU operation, 4-bit or 2-bit or whatever we want to generate, and that's it, right? So that's the straightforward option, makes things simpler to understand. The problem with this is it's not very efficient. Why? Because essentially for this, the controller needs to go 2 steps. One is needs to check the opcode, then it needs to go to check the func3 in the same controller design, and then that makes things a slightly more time consuming to generate other control signals. So we do it in 2 steps, okay? We do it as the following. In the controller, we check the opcode. There are only 3 possibilities, okay? Either we need to do add, or we need to do sub, or this is an R type or I type instruction and we don't know what exactly this is. That is, go and check func3, func7 kind of thing, okay? So in that case, since we don't know that, we can basically generate 3 code. So for example, we can say add is 0, 0, sub is 0, 1, R type, for example, is 1, 0. If I also want to do I type, I can actually do I type 1, 1, okay? So in the controller, I basically create these 4 type of signals. I see a store word or load word, I do 0, 0. 0, 0 means I want to add. I see branch equal, I issue 0, 1. 0, 1 means I want to subtract. I see an opcode that belongs to the R type instruction. I don't know exactly which one going to be. It might be an add or sub, or it might be something else. I issue 1, 0. That means that go check func3 and you will figure it out. And then I see an I type, I do the same. I issue 1, 1 and say, okay, again, go to func3 and figure it out. Okay? Then for those one that are go figure it out, this is 1, 0 and 1, 1, we basically look at the func3 and func7. Okay, so what is func3 and func7? Then you can see, for example, for add versus or versus and, I see that, okay, 0, 0, 1, 0, 1, 1. For example, if I see 1, 1, now I know for sure that this is an and operation. So I issue an and control signal. If I see 1, 1, 0, then I know that this is an or operation. So I issue that. If I see 0, 0, 0, I go and check this last bit, and then I'll know what exactly happening. For I-type instructions, same story. Basically, if I see 1, 1, 0, as you can see, it's still or. So all I need to do is just look at the func3, and then I'm good to go. Okay? All right, so this is how we do it. Okay, so here we issue this 2-bit value, which is 0, 0, 0, 1, 1, 0, or 1, 1. And here we take this value, we look at the func3 and func7, and then we issue our final 4-bit value here. Okay? So this is the story here. The ALU control, I can basically do the following. Like I can do 0, 0, 0, 0 for add. I can do 0, 0, 0, 1, for example, for sub. I can then, for R-type instruction, I concatenate 0, 0 with some, 1, 0, 1, 0 plus whatever value. So for example, I can say add is 1, 1, 1, 0, 0. Could be for add. 1, 0, 0, 0 could be 0, 0, 1 could be for sub. 1, 0, 1, 0 could be for and then 1, 0, 1, 1 could be for or. And again, these are just internal. There's no standard for it. So feel free to change this any way you want. You can actually follow it. I think book has a specific mapping, but you can follow anything you want. Okay, and then you can do the same thing for an immediate. Does that make sense? Yeah. Yeah, so again, so here I have the opcode. I can basically decide whether this is an R-type instruction, an I-type instruction, a store, a load, or a branch. Yeah. Yeah, as you can see here, right? Yes, which one of these type of operations are we seeing, right? So are we seeing this group? Are we seeing this group? Are we seeing this, or this? As you can see, groups are having the same opcode, right? So this one. So I can basically distinguish between these 5 different groups, okay? So yeah, so I issue the ALU op accordingly. If I see load or store, I know this is an add, okay? So I issue 0, 0. If I see a branch, I issue 0, 1. It means that this is going to be sub. If I see these guys, I don't know which one it is. So for this one, I issue 1, 0. For this one, I issue 1, 1. Okay? And then this is passed through the ALU control. The ALU control sees these numbers. If it sees 0, 0, easy. This is an add. I can just add another 2 zeros and this becomes add. If I see 0, 1, also easy. This is a sub. I can also, again, like do it this way, right? If I see 1, 0, that means I need to go and check out func3. Based on func3, I'm going to issue a number. If I see this is an or, for example, I put 1, 0 and I put 0, 1, and this would be, for example, this is just a contract between the ALU control and ALU operations. So it's just arbitrary, you can map it, okay? In your project, you're going to do the same. We want you specifically to do it in 2 steps. And then again, mapping is your choice. Whatever code you want to do it, that's your choice, but you have to do it in 2 steps. Yeah. Correct. So store word, load word, BEQ. And then you're going to later see, for example, if you have different type of BEQ, then we might need to then go back to this and change that if we need to. If it's a different type of store or loads, though, always it's an add. I don't need to do anything else. Okay. Any questions? Yes. Exactly. So it's not standard that this, but standard is usually doing it in 2 steps. But like what exactly is the numbers is not a standard. Like if we want to do 0, 0 for sub, you can go for it. That's fine. All right. Okay, so that's kind of like cover everything we wanted to cover for microarchitecture part. As I said, you're gonna actually implement this in your computer assignment number 1, and you're basically gonna go through this process and code this. So there you're gonna actually see a lot of these decisions that we made, and this would be a good practice for you to kind of like go back to all of these things. You need to also come up with the mapping and all that. I want to finish this part of the lecture with just going through the steps required for each of these instructions. So for an R-type instruction, basically what I'm showing you here is that things that are grayed out is that they're not going to be used during this instruction. So for an R-type instruction, let's see what happens. As I said, the positive edge of the clock comes and the PC gets updated, right? The PC gets updated, and that means that we're gonna put a new address in the instruction memory. That will result into new instruction, okay? The new instruction comes out, and as a result, all of these lines gets updated, right? So all of these lines gets updated at the same time. One thing that I always say when I'm explaining this is that think about this as flow of water, right? Think about your registers as kind of valves or gates, and then think about the clock as an opportunity to open these gates. Okay, so the clock comes, you open this gate for a brief moment, new water comes. Rest of it is, think about this as pipes. Okay, so water comes and goes through all of these pipes at the same time at the same latency. So it's not like one after another, but rather it's everything happens at the same time, the way that the water flows in pipes. Okay, so these are parallel pipes and the water flows to them. Okay, but their paths are different. So for example, this pipe goes through this path, and then again it branches out to many different paths. Depending on the path it goes, the time it takes to generate that result might be different. For example, if I put this value here, and I want to read register 1, the time it takes that this value gets updated might be very different than the time it takes for this value gets updated. It might be different than the time it takes for this value to get updated, and so on and so forth. Okay? So just keep in mind that, again, things get updated at the same time, but as we move from left to right, depending on the path that they need to follow, their time actually are slightly different. Okay? But eventually things reach, from different paths, things reach to the point. So for example, from this path, you have your immediate generation, and the value goes here. And then from this path and this path, values goes here. For R-type instruction, we don't care about the immediate generation. So it's going to be active. It's going to generate a value, but that value is not going to be used. Okay? But everything else is going to be used. So these values gets updated, ALU source gets updated. This value will be available as an address, but since the read mem and write mem are 0, the memory is not going to be active. Instead, this path is going to be updated. Again, the mux is going to select this path, and this path will get updated. This value with some delay is going to get updated. In parallel to these guys, this value is going to get updated, and then this value also will get updated, but since we are going to choose this one, we're going to go this path. and then we're gonna have our final results here. So everything happens in parallel, but at different timelines because they have different paths. Eventually, by the end of the clock cycle, all these values should be settled, right? So all of these things should be settled at one particular number. And then by the next time that the next clock cycle comes and we open the gate again, all of these values are settled. If they're not settled, then you're going to run into issues of correctness issues, okay? So your clock cycle should be wide enough and long enough so that you let these things to settle down and all the values get updated, and then the new clock cycle comes, okay? Same story with load word. So for load word, again, starts from here, goes here, all these things gets updated. For load word, by the way, these are typos, so these should be 32. For load word, we're not reading the second register. Again, we put a value and we read something here, but we don't care about it. We discard it. We read the value from here. So we put it here, here. We put the results here. Again, we put something here, but we're not going to select it. We're going to put things here. We read the value here. So there's actually, we need to wait for the memory. This value gets updated, and then this value gets updated. Similarly, this value going this path, and this path. Okay? That's for the load board. And then you can actually do it for others as well. Actually, in your homework, we're going to ask you to compute the delay of each of these instructions. We're going to give you the value of each operation. Like, how long does it take, for example, to read from the memory? How long does it take to add to those two numbers? How long does it take to generate an immediate, and so on? And you have to calculate the entire end-to-end time. Someone had a question? Yeah. Yes. If you want to read it from memory, also has to happen in within one cycle. Within that clock cycle, yes. All of these blocks operate. So most of them are actually combinational. They don't have clock, right? So the only thing that has a clock here is the PC at the moment. Everything else is combinational, right? There's no clock here. So you just put the clock on PC and everything else just move forward. Any other questions? Perfect. So that's it for our microarchitecture. Let's have like just a 2-3 minutes break, and then we're gonna start the next one. Okay, so now I want to talk about, now we understand the basics of the ISA. Now we also managed to map a simple ISA, a subset of a simple ISA to a microarchitecture. Let's see how to improve this. What are the things that we need to care about for a modern system? How do we improve this, and how do we use this in real systems? Because this is kind of like a toy example for you to understand. The fundamentals are the same, but then we're going to add tricks and more features. Generally, as you will see, the base is this, and then we're going to add more and more things to this CPU. So fundamentals of any modern CPU is kind of like data path controller, kind of different path, different components within the data path, and so on. It's just the features that we are adding to our system are getting more and more advanced. You just add more things to your architecture, and then you will have a more modern and more advanced system. Bunch of logistics before we moving on. As I said, CA number 1 will be released this week. Will be based on the microarchitecture. The deadline would be before your quiz 1, so that you kind of practice the design. It will be based on C or C++. You have to write the code and then submit it to Gradescope. There will be tests on the Gradescope sequence of instruction. Your simulator kind of quote unquote simulator should generate the correct result of that. That basically would be the project. We also will release homework 2 sometime soon. We started the discussion sessions this week, so please go and check it out. My office hours on Tuesdays. Please please attend the office hours if you have any questions. Yes. Oh, okay. Let me. Is it better now? Okay. All right. And then my office hours is in Bolter Hall on Tuesdays. If you want to have one-on-one office hours with the TAs, there are two options. Either go to the discussion sessions. I ask the TAs and LAs to dedicate it some time for just answering questions. Usually the first 10-15 minutes of any discussion session is just if you have any questions about the lecture or the homework, you can ask that. If you need further time, you can always ask for one-on-one meeting with the TAs, message them on Campus Wire, and they're more than happy to schedule a one-on-one time with you if you want that. Someone had a question or yes? Uh-huh. Yes, so you get unlimited number of submissions. So you can, the question was about how do you test your code on Gradescope? Yeah, you can just basically run multiple submissions. You can go to any of the discussion sessions that you want. Yes. All right. So as I said, we talked about single cycle processor, a simple and easy design, but not the most efficient. Why it's not the most efficient? I kind of talked about this and someone actually asked about, oh, do we actually need to wait for the processor to read things from the memory within the same cycle? And the answer to that is yes. Actually, this is, if you think about this, is that I told you that depending on which path the data goes into the processor, your clock cycle should be long enough such that all the different paths are settled. So you're essentially bounded by the longest path in your design, okay? This is usually called critical path, okay? So the critical path is the longest path among all the possible paths in your design. In any logic design, this is the same thing. Processor is also another example of a logic design. You have to see what is the longest among all the possible paths. Your clock cycle should be bigger than that, okay? To ensure that the system works all the time, okay? So in our design, actually you can, as I said, this will be a homework for you that you can actually compute the path for different ones. But it's clearly, you will see that the load instruction is the longest one. The reason for it is that if you actually look into this, for the load, you have to basically go through these paths. You have to go through the register file, you go through the immediate generator, you go through the ALU, and then you have to actually access the memory and then get the result of this and then write the result back. So you have to wait for ALU, you have to wait for the register file, you have to wait for ALU, and you have to wait for the memory and then be able to write the results back. So there's like 3 big components that you need to wait for. And this, unfortunately, is very, very slow. And now even we simplified the memory. We told you that, oh, memory is just within 1 clock cycle away, so you can actually instantly read it. But in reality, reading from memories could be hundreds and hundreds of cycles. And then the bad thing about this is that you cannot have a dynamic clock cycle, okay? It's not like, oh, if this is an add, I clock faster, and if it's a load, I clock slower. Clock is a deterministic thing that is generated by analog circuitry, and you cannot change the dimension and the period of a cycle, okay? So if your load is the slowest, everybody will be penalized. So all the instructions will be penalized because everybody should be with the same speed of the slowest among the instructions, okay? This means that essentially the system will be as slow as how long you are reading a memory. And memory is also, as I told you already, it's very, very slow. So single cycle design is not very, very fast design. It's very simple. It's easy to understand, but it's not a great idea to do it because essentially you're penalizing every single instruction by the slowest instruction that you have in your IC. Does that make sense? Okay. Yeah. So can we do better? Any suggestions of how to make this thing faster? Separate the memory cycles somehow. How do you do it? Okay. Good suggestion. Anyone else? Yes? Say it again. Multi-threaded. Okay, so you have multiple, so you replicate this data path, and then, for example, if it's an add instruction, you feed it to the faster ones, and then, okay, that could be very expensive, but it's possible. Any other suggestions? Yes. Press that instruction. How would you press that instruction? Okay. Any other suggestion? You can, so the suggestion is somehow parallelize things so that, you know, one instruction does memory read while the memory is happening, maybe you use other parts of the memory. Okay. Yeah. These are all good suggestions. Any final suggestion? Yes. Out of order execution, it's one step further because now I'm just talking about the single instruction. So the first instruction, like all the instructions, even if we don't have any problem of dependency and all, we still, everybody will be as slow as a load, right? So, but yeah. Yeah, you can do it in stages, and it's kind of like similar to the parallelism idea that you can decouple these stages from each other so that if you're waiting for memory, maybe you can get to use the rest of the CPU, put it to utilize the rest of the CPU. Yep, that's basically what is happening, and you're gonna actually see the results. So short answer is yes, you can. The first thing that you can do is doing what we call multi-cycle. Multi-cycle design is when you are dividing the CPU into multiple stages. You don't clock, you don't wait for the entire thing to finish, but you say that, excuse me, you say that, for example, reading a register is one stage, and I clock it. So I add, I separate this from the memory from the ALU and so on and so forth. So I divide it into stages and then do it separately in each stage. This way I can, for some instruction, it takes more cycles to finish. For some instruction, it takes less cycle to finish. Things like that. Or you can actually parallelize it later, as we're going to talk about the pipeline. I'm not going to give you the detail just yet. That would be the lecture next week that we're going to actually talk about this microarchitectural changes that you need to do. But I want to actually take a step back and tell you a little bit about if I have multiple of these designs. So you suggested various different things. Someone says, oh, add more things to the data path. Someone says, add more cycles. So how do we actually measure the goodness of these suggestions? Like, how do we actually quantify that one is better than the other? Okay, this is the story that we want to talk about in the rest of this lecture, and that is how do we measure metrics such as performance and power and so on. Remember that, again, the goal is making efficient computers, and if you remember, we said that mostly the goodness of a computer in terms of efficiency is how fast we can run things. Okay, so there are two things that we usually care about a lot in computer architecture. The first one is latency. The second one is throughput. Latency latency means that how long does it take for a task to finish? In case that we are talking about how long does it take to finish one instruction, or you can actually think about how long does it take to finish, let's say, 100 instructions. Or more generically, how long does it take to finish a program that might be thousands and thousands of instructions? Okay? And of course, the lower is better. The sooner we can finish one instruction, the sooner we can run one program, the better the computer is. The second thing is the throughput. The throughput is, for a given time, how many tasks can you finish? Okay? And for throughput, the higher is better. Basically, throughput is usually a rate number, right? So you measure the number of instructions per cycle or number of bits per second and things like that. Okay? There's also other metrics, and again, this depends on the application that you're looking at. For example, if this is a low power application, then how much power are you using to achieve the latency that you want? Okay, so for example, there are these metrics like performance per watt. Okay, performance per watt, which means that, okay, you have a method that can make the computer 2 times faster. Great. So performance is great. But it also means that it's increases the power consumption 10 times more. Okay? So if I actually look at the performance per watt, the performance per watt is not increasing, it's actually decreasing, right? So you have to also care about these metrics. Same story with energy, which is kind of product of the power and latency. So you want to reduce the energy. Which one is more important depends on the application level and the device level. If this is the latest and greatest thing that you want to put in a server to run a large language model, you probably care about latency and throughput. If this is like, for example, AWS server, you just don't care about latency, you also care about throughput because you want to be able to, run multiple tasks at the same time. If this is an Apple Watch or an iPhone, then you also care about power. You don't want things that are just fast. You want things that are fast and power efficient. So there are these considerations that you need to make when you're designing these stuff. One question that always comes up when we are talking about throughput and latency is throughput and latency essentially the same thing? In other words, if I say, I can do T tasks, it takes T seconds for one task, does it generally means that the throughput is 1 over T? Or in other words, if it takes T capital seconds for N tasks, does that mean my latency is basically T over N? Anyone wants to answer this question? Is the throughput and latency are essentially interchangeable or not? Yes. If you parallel things, it won't be the same, or it will be the same? It wouldn't be the same. Yes. So exactly. So if there is some form of a concurrency happening, then these two notions are not the same. So here's an example, for example. If I want to run 3 tasks, and tasks runs like this, that the first task takes T1 second, task 2 takes T2 seconds, but the majority of task 2 is basically overlapped, then the entire thing takes T capital second. But as you can see, the individual one, so it's not like T1 plus T2 plus T3, but rather it's some form of an overlap between them, okay? So if there is a concurrency, then the throughput and the latency are not the same thing. That's why both latency and throughput is very important for us. If there is no concurrency, then there is no difference. The latency and throughput is basically interchangeable. 1 over latency is your throughput, 1 over your throughput is your latency, okay? But in most systems, since we have multi-core or multi-threading, we have parallelism at the instruction level, at the program level, then both throughput and latency are important factors for us, okay? There's also a few things that you're going to see in this class and generally in the kind of jargon in computer architecture, and that is when we are saying things like we improve things by 2.5x or we improve things by 2.5 times. what that means is that whatever it was, we improve it by, if I want to show it in percentage wise, it means that the improvement is 150%. So it's basically 1 plus 1.5. That's how we say things are better 25%, 25.x. And then another thing that you always like, you might be confused is that when we use the word improve depending on the context. So when I say, for example, I improve the latency, it means that I actually decrease the latency. If I say I improve the throughput, it means that I actually increase the throughput. So just be careful about the metric, and when you say improve things, what do we mean by that? Okay? The second thing that I want to talk to you about is the notion of time. Okay? So for example, I told you that for latency and throughput, we measure time and the number of tasks, and that's how we compute the latency and throughput. Just keep in mind that the way that we measure time is very, very important. So generally, we use time to measure the performance, which means that for the same amount of work, the computer that has less time to finish it obviously is the fastest. The way that we measure the time, though, is a little bit complicated. Okay, so if you want to measure time, time is basically like any application that you're running in a modern systems is a composition of multiple different things. So first of all, what we can measure at the user level. So think about like you're running an application on your Windows machine or a Linux machine, and you're measuring time. The thing that you're measuring is called wall clock time. It's the time on top, okay? But that time is actually divided into a bunch of different things. It divides into the system level activities, for example, reading the I/O, computing the system calls and all that. Then it's actually running the application that you want to run, but that application itself has some time for reading and writing things from the I/O, the input and output, and then for the computation, okay? The time, and then to make things even more complicated, most of these systems are multi-threaded, and then they run multiple applications at the same time. So sometimes the operating system needs to context switch. So it needs to pause your application, run another application, then continue your application. From the user level, you will not notice this context switch because the context switch happens very quickly. But in reality, there are times that your application is actually not running. So long story short, what we really care about when we want to, like, for example, change something in the processor, in the microarchitecture, and make things faster, we're essentially just addressing that compute things in here. But the measure the time, we are actually measuring a bunch of other things. Okay, so our notion of measuring time is very noisy in most cases because there are a whole bunch of other things happening in the background that's also contributing to this overall clock time. Okay, just keep that in mind. So when we say time and CPU time, we are focusing on this. How do we optimize and measure this? How do we reduce the context switch and all that? That's not something that you're worried about in this course. That's something that you're worried about when you're designing your operating system and the system in general. So we're not going to focus on those other aspects of the system. We're only focusing on this aspect of the system. Later on, I'm going to give you a short lecture on the I/O, and you're going to see a little bit of the rest of the system. But for now, our main and sole purpose and goal is just reducing that compute time for that particular program. Okay? The other question? Yeah. Yes. So essentially, the elapsed time is this plus this plus this plus this plus so many other things. So times for the I/O is, for example, let's say you're pressing a key in your keyboard, the time it takes actually for your program to read that value and do some action on it depends on how long this process takes. It's actually very, very slow process. Similarly, for example, if you're browsing your internet and you're running some application, that's kind of interact with this browser. The time it takes for the network packet to receive the packet, and all of that is your I/O time. Good question. So the question is, are these also computer architecture? It is to some extent, but it also talks with the network and the operating system. So it's a system level optimization. But there are things that you can do, for example, on the computer architecture side to make those things faster as well. So for example, you can design a network interface card that is better. So there are a whole bunch of research actually at the moment that is very hot topic, and that is that if I have a bunch of servers, let's say I have 10 H100s and I want to run a massive model, how do I train this? Because there needs to be a lot of, not one model can be fit into one of these GPUs. These things needs to communicate to each other. So there's a whole bunch of things that each level of GPUs, but there are a whole bunch of things that they need to talk to each other. So how do I actually design this? And you can actually design hardware for it. You can design stack for it. So these are all lots of things that is happening at that side. But yeah, it's outside of our main focus at the moment. So what do we care about is CPU time. What we can measure most of the time is this time. There are ways that you can kind of like from there get to there. I'm not going to get into it, but let's actually focus on CPU time, okay? In order to measure time in general, including CPU time, in computer architecture, what we really like to do is two things. One is we really love simulation and generating simulation tools. Why? Because measuring these times, given that these complications, is very difficult to do. And then if I want to change hardware and see the impact of like changing hardware in this time, it's also very expensive because I need to go and tape out a new chip and then measure time. And then I need to, for example, make another small change in the CPU microarchitecture. I'll have to go and tape out the chip again. So I don't want to do that. Instead, what we do is that we use these simulation tools. Basically, simulation tools are these software programs that kind of mimic the behavior of the CPU itself. That's actually what you're doing in your CA1. You are basically writing a high-level C code that kind of mimic the behavior of the CPU. So for example, you're fetching an instruction. You're not really fetching an instruction. You're basically calling a function, using arrays and all that in C, but you can mimic the behavior. And if you can then assign times to these behaviors, you can then measure how fast your system is. The value is not going to be, like the absolute value is not going to be accurate, but the relative value will be accurate, right? So for example, if you double the size of the memory, you can see that how low the number of operations, how much of your number of operation changes, and that will help you to kind of have some form of estimation. So in the engineering teams, there are a lot of people who are just working on simulation and emulation side of things before actually going and taping out the chip and making the chip, okay? Just keep that in mind, yes. So the question is that which level of simulations you can do. You can do circuit level simulations. You can actually do macro architectural level simulations. So again, your CA1 is an example of a simulator. It's a simple simulator, but it's a simulator nonetheless. That you take, I give you this design, you write functions that basically mimic that behavior, right? So in modern companies, like Intel has some form of a simulator like that. It's much more complicated and advanced, but it's very similar, kind of practice. High level language, exactly. Yes. Fade out. Fade out.
You might
Yes. So the question is, when you're kind of like moving up in the level of abstraction, you're gonna lose some of the semantics. For example, at the C level, you're not gonna see the parallelism that you have inherently in hardware, because things at the C level are naturally sequential, right? So yes, there are actually things that when you're actually doing your CA1, you're going to see that you're calling functions one after another, but in fact, these functions are parallel. So how do you fix those things? That's actually would be a challenge for you guys to think about. But there are tricks that you can do, but there are things that you cannot generally capture. And this is a trade-off. But it's a nice thing about simulators that it's quick, right? So you can actually write a C code. You know, changing something in the simulator is just changing a function. Changing something in hardware means 6 months of work of taping things out and so on and so forth. Real products doing all of that. So it's doing simulation, doing low-level circuit simulation, lots of verification, taping out, post-tape out, they actually do lots of tests. So that's why it's very expensive to actually generate a new code, but these big companies have thousands and thousands of engineers to do that. All right, so that's one thing that you're going to see. Simulation is very, very important in computer architecture. The second thing is that, okay, let's say I have a simulation or have a design. How do I know that this design is actually good? How do I actually compare this design versus other design? What is the methodology? For that methodology, you need what we call benchmark. Or benchmarks is basically a group of standard applications that you use in order to test your behavior of your system. Benchmarks needs to be very carefully designed such that it can actually look into various different parts of the system. So, for example, you need a benchmark that has lots of writes and reads to the memory. You need another application that does lots of ALU operations. You need another application that does lots of the branch operations. You need something that is very carefully designed so that it can stress test various different aspects of the system. And it's not something that you can come up with. Sometimes you can, but mostly these are standard benchmarks. So for example, some of you have heard about SPEC. SPEC is actually kind of the gold standard in computer architecture. There are different versions of it, like SPEC 2000, SPEC 2006, SPEC 2017. This is actually kind of a consortium that comes up with a list of applications that people use in order to test their programs. So just keep that in mind that benchmarking is very, very important. Actually, if you look into, like, if you follow, for example, the new generation of the GPU, NVIDIA GPUs, or Apple Silicon, and so on, what you will see is that the first thing that they do is that they run some benchmarks and they report the results. They say that, oh, this generation, when I'm running this benchmark, is 2 times faster than the previous generation. That's how they actually report these numbers. It's important to have something standard. Okay? All right. So going back to the CPU time, the last thing I want to talk about today is actually what are the important components on my CPU time? Okay? So let's say I want to somehow will measure it. And again, this is a story of how do you measure it. You may not see this in your career depending on what you're going to do. But let's say I somehow can measure the CPU time. What are the important factors at the microarchitecture level that decides how CPU time changes? And this is what they call iron law of the processor performance. The iron law of processor performance, it basically says that your CPU time is a factor of is based on 3 important factors. It's the instruction count, it's the cycle per instruction, and it's cycle time. So let's actually look at them one by one. Instruction count, or IC, this is basically saying how many instructions are you running on this program, CPU. Effectively, the more instructions you run, obviously it takes more time, right? So if you're running a very complex algorithm, your CPU time will be high. If you're running a simple algorithm, your CPU time will be less, okay? So what is the impact of CPU time? How we can optimize CPU time? There are 2 things you can do to optimize your CPU time. Number 1 is if you use better algorithms, you can reduce your instruction count, right? So you have learned about complexity of algorithms in your 180, for those of you who have taken an algorithm course. We talked about, things are O3 or log n or n squared. So the simpler your algorithm is, the less number of instructions you're going to have. As a result, your system is going to be faster, okay? The second thing is if you use different ISAs or different instruction within that ISA, or if your compiler can generate more compact programs, your instruction count can go down. Okay, so the role of the compiler is very important in the IC. The role of the ISA is very important in IC. In fact, one of the key areas of research in ISA is creating what they call custom instructions. Okay, so for example, if I see in my program that I have sequence of, let's say, 4 instructions that's keep being repeated. Okay, what people usually do is that they make these instructions into one instruction. So they add more support in their hardware, they add more of things into their data path, so that these 4 instructions is one instruction, and that way they reduce their instruction count and things run much faster. Okay, so there's trade-offs like this that you can do with the instruction count. Okay, the second thing is what we call CPI, or cycle per instruction. CPI also usually referred to as IPC, or instruction per cycle, which is 1 over CPI. So CPI and IPC, similar thing. There's also sometimes people refer to this as MIPS, or million instructions per cycle. Generally, IPC or CPI is the measure of how long does it take to finish one instruction. So how many cycles do I need to finish one instruction? So far, what you have learned is that your CPI is 1. Your single cycle design is basically give you 1 for every single instruction. Okay, but what you will learn later is that there are some instructions that their CPI might be higher. When we are actually at parallelism, you can actually reduce the CPI to even below 1. If I can run multiple instructions within one cycle, essentially my effective CPI goes below 1. Okay. There are different things. For example, some instructions might take more cycles and so on and so forth. Lots of things that we're going to talk about is basically reducing that CPI. Last thing is your cycle time. And cycle times is depending on 2 important factors. One is how fast your design is in general. And that is the transistor technology that you are using. That is the logic design that you're using so that you can clock things faster. The second thing is the path, the critical path in your design. The lower and smaller the critical path is, the faster that you can clock things. So the lower the cycle time is. So there are 2 important things that you need to care about. One is the technology that you're using, and second is reducing your cycle time. Okay. Any questions here? Yeah.
The cycle per instruction varies for each instruction. So it can actually would you not actually if the instructions are different CPIs?
So the question is, if different instructions have different CPIs, how do you calculate this? So you have to do the averaging, right? So you will do, so your CPI is the sigma of this across all the instructions, okay? So you basically compute the effective average CPI, and then from there, you basically measure the CPU time. Okay, so what we want to do now is, taking now that we understand that we want to reduce the CPU time, then we're going to introduce new architectures or new techniques to reduce the CPU time. So we start with single cycle. We say that single cycle is nice and simple, but it doesn't give you the best performance. So eventually we're going to get into the pipeline design that we're going to describe next week. And you will see that how pipelining is going to help us to overall reduce your CPU time. Okay. Before that, though, there's one thing that is kind of like one step between single cycle and pipeline, is what we call a multi-cycle or multi-stage design. Essentially, the idea is that you take a design like this that we covered and you break it into stages. For example, I draw those kind of dotted lines. And now what I'm doing is that I'm basically divide what used to be entire thing 1 cycle can be now 1 cycle here, 1 cycle here, 1 cycle here, 1 cycle here, and 1 cycle here. So I designed this 5-stage thing that basically breaks down things into separate stages. So how does this basically helps us? Remember I told you that think about your registers as gates, and then basically the activity as floating of the water. So essentially I'm adding more gates, okay? So at every clock cycle, I'm closing the gates and opening them one by one, okay? So basically the water starts from here, the charges goes to here and stop here. At the end of the cycle, things needs to be stable at this point. I no longer needs to wait everything to be stable. I just need things to be stable here. Yes. Say it again. Question is, wouldn't this make the entire thing slower? Let's see. So for now, oops. For now, what we are doing is that for each stage, I essentially break down what used to be I need to wait for the entire thing to finish, to that I need this thing to this thing to be stable, this thing to this thing to be stable, this thing to this thing to be stable, and this thing all the way back to the register to be stable. So what I will get as a benefit of this approach is that my cycle time will shrink significantly, okay? So my cycle time, which used to be this plus this plus this plus this plus this, is now one of them, the largest among them, right? So because these are all happens at the same time, whatever is the largest is now my new clock cycle, okay? So I can clock things much, much faster, okay? Would that help us or not is the story that we're gonna see later. For now, it wouldn't, because it's still each instruction has to go through all of these stages. But once we introduce the notion of pipelining, you will see that now we can actually get benefit from it. Yes. Question is, what is the difference between this and pipelining? Pipelining means that now I basically introduce instruction and feed them into separate stages separately. So for that, I need to also take care of my controller, and I need to change my data path. Here, I'm just breaking down things into registers. So I'm only introducing registers in my data path. I'm not changing anything else. Yeah. We only get a speed increase when we have pipeline. But if I somehow can skip things, right? Then I can also get a speed increase here, because remember I told you that clock cycle was determined by the memory, but here the clock cycle is no longer determined by memory, right? It's determined by whatever the max of these stages are. So I mean, at best you can clock things 5 times fast. And then again, the reason that this works is, again, for those of you who remember, this is kind of the general idea of sequential and combinational logic. So usually we sandwich a combinational logic between 2 registers. This way, basically what it means is that the period of my clock should be the delay between starting from here all the way to here, okay? So if I want to reduce this delay more and more, I basically add more registers to this combination. Now my delay is this much. If I break it even further, my delay is this much and this much. So I can add more and more registers to break down a long path to a smaller path, and this way I can clock things faster. Yes. Great point. So actually, I'm going to answer this right after this slide. Okay, so first of all, this is the design that we're going to go after. But your question is this: that okay, how much can we break this down, right? At some point, you cannot break this down any further. It's like, think about it as a kind of a quantum effect. That's like at some point there's nothing else that you can make it shrink it any more. And that's why we are actually looking at 5. The idea of 5 here for this particular pipeline is a balanced design, that you want to roughly each stage takes the same amount of time. Otherwise, you're wasting registers, right? For example, if I add another register here, if this time is like if the clock cycle is already determined by this, there's no point of adding more registers. You're just wasting area, wasting power, and so on. So the way that we do this and we make this 5-stage thing is that we roughly make things equal size. So essentially the time it takes to read memory is fairly similar to the time it takes for reading things off of the register and adding them together, roughly the same time from reading a register file and all that. Okay? So these are the registers that we are dealing with. And later next week, when we are talking about pipeline, we will see these stages. This is what we call a fetch stage, okay? This is what we call a decode stage. This is what we call an execution stage. This is called mem stage, and this is called write back stage. Essentially, write back is when we are writing the data back to the register, okay? And these pipeline registers, or these registers that we put here, is named after the stages that they are representing. So this one is instruction fetch, instruction decode pipeline. This one is instruction decode execution pipeline. This one is execution memory pipeline. And this one is memory write back pipeline. So we're adding these 4, and the 5th one is basically this PC. So PC is basically act as the 5th pipeline stage of this. So you have 5 registers, and these are all synchronous, right? So the clock comes, all of them get updated at the same time. They update their corresponding output, and then everybody basically moves forward with that. Okay? Questions here? All right. We also show it this way. So this is also something that you will see a lot next week. So in order to, instead of showing this fairly complicated design, to kind of make our life a little bit easier, we kind of show it this way. So this is your instruction memory. This is your fetch state. This is when you're reading it from the register file. This is your decode stage. And by the way, your controller also sits here. That's why this is called decode, because that's when you decode the instruction. This is your ALU stage. This is your data memory stage. And as you can see, you can also bypass the data memory if the result is coming from the ALU result. And this is your write back stage. And as you can see, this is a still register, but this time is writing to the register, not reading from the register. Okay? And this gray things are your pipeline registers. Okay? So this terminology, you're going to see like this way of mapping things is what you're going to see later as well. Yes? All stages update at the same time. Yeah, the same clock cycle goes through all of them. Mm-hmm. Okay, so now going back to what you asked, does this even help in our design? Let's see what happens. So if we are just, let's say, the only thing that I do is doing multi-cycling, okay, that essentially I'm just dividing the long thing into smaller thing, what will happen is if I look at the CPU time and the iron law, let's see what happens. So first of all, instruction count doesn't change, right? So adding pipeline stages does not change your program or the number of instructions that you have in that program. Excuse me. What it does change though is the cycle time. So if I do a balanced design in an ideal case, if I break down a big thing into smaller n pieces, I basically reduce the clock cycle by a factor of n. In this particular case, if I'm going with the 5-stage pipeline, my new cycle time essentially will be 1/5. Okay? But what happens to your cycle per instruction if I do multi-cycle? So IC stays the same. My cycle time reduced by a factor of 5. What would be my cycle per instruction? it goes up by 5, right? Because now what used to be 1 cycle, now it takes 5 cycles. So it's kind of like go 1 step, 1 step, 1 step, 1 step. So effectively what will happen is that technically nothing changes. So you're not going to get benefit nor you're going to lose time. In fact, you're actually going to slightly lose time, because what will happen is that reading and writing to these registers also takes time. So it's not like, your single cycle was slightly faster than the pipeline design, because pipeline requires some time for reading and writing. But you can this is a negligible time. So, I mean, roughly it stays the same. Yes. Yeah, updates at the same cycle. Because again, so it's like this, right? So your instruction comes to the instruction memory. So it updates this value, but its registers are not transparent. They get updated in the next cycle, right? So this value, so you start from here, this value updated, this value gets updated, but then it waits until the next cycle comes. Once the next cycle comes, then this one basically goes here. And then this value gets updated, and then everything else gets updated, and then it waits. And then the next cycle comes, and then this one goes here, and so on and so forth. So your combinational logic goes through, it waits until the next cycle comes, and then moves forward. So if I didn't have the registers in between, it would have been all combinational. So it all moves forward, right? So it would have been, so if I only had a register here and register here, clock comes, this value gets updated, after some latency, all the things get updated. But again, think about registers as your gates. Your gates is closed. It only gets updated when the clock comes. So then the next part of the system gets updated. Okay? Yeah. So that's what we are trying to say here, that we are not, so the question is that if these things are not in parallel, then how do you get advent? You don't, right? So it stays at 1. So that's the point of, okay, we need to do extra in order to get this below what we want. So we want, ultimately what you want to get is 1/5. So if I somehow magically I make this 5 equal to 1, then I'm going to get the benefits. I'm going to make the system 5 times faster. And that would be how we're going to do the pipeline. That we need some form of a parallelism, but for that, we need to add a little bit extra to the system. Any other questions? Okay. So kind of like, the summary is multi-cycle increase your CPI, but it also decreases your cycle time at the same time, and overall performance does not get better. So in order to fix this, we're going to introduce the notion of pipelining. That is, we can run multiple instructions all in the same data path. So like one instruction could be in the fetch, another instruction could be in decode, another instruction could be in the execute, and so on and so forth. So we make the things such that it's like 5 times faster. So we actually kind of overlapping things. So we increase our throughput, and by increasing our throughput, we can actually reduce the latency. So we're going to talk about that in the next week in the next lecture. Okay? So that's it for today. Thank you.